Hi everyone. It's still it's 4:55. Once again, I'm going to wait a minute for folks to come in. I actually can't see what I'm sharing when I do it this way, so I'm trusting y'all to shout if it's not working correctly. All right, it's 4:56, so let's get started. So thank you, first off, for the 3 folks who already went ahead and submitted their homeworks. It's great, even though I technically haven't told you everything. I see many people are looking for resources online to help fill out gaps in Haskell knowledge. That's great. There are some links in the syllabus on Brightspace that you can also look at. And also Haskell is pretty well documented throughout the internet. So if you do a Google search, you'll also find relevant things. So today's class, we're going to keep live coding Haskell. I'm going to hit some of the topics that I didn't have time to do in last lecture and start talking a little bit about higher order functions and, how to like write code, especially involving lists because there's a lot of lists in the homework and lists are a really nice vehicle to study a lot of things before we look at arbitrary algebraic data types. They're a really nice setting to like look at a lot of the features that Haskell works really well on. But before we do that, I want to take a minute or two for everyone to think about what they want to hear about in this live coding session. And I want you to write it into the chat. I don't know if you can do it anonymously. Oh, you can send it to me if you're feeling shy and you don't want to let everyone in the class know. Just chat me in the chat. Twitch, feel free to do this as well. About what one topic, it can be 3 words, 4 words, you want to see more of. Maybe you started working on the assignment and you looked at it and you're like, how do I do this? Or, I'd really like to know more about, say, list comprehensions. That was the most voted topic last year 2 years ago when I did this. And so, so just take a minute, think about it, and just go ahead and type it into the chat. I'll be waiting for you all. I see one person wrote importing modules. Syntax and recursion. Yes, recursion is definitely something that I do want to talk about in a lot more detail. And yes, syntax is, it's like, it feels silly, right? It's like, I feel like I know how to code this, but I can't get the compiler to accept things for me. But actually, Haskell syntax is kind of unconventional, so I can see it as a challenge for some folks sometimes. I see someone requesting lambdas. If we get enough to higher order functions, we'll definitely talk about lambdas. And we'll definitely talk about it in a lot more detail when we actually go and talk about the lambda calculus. There's a write-in from Twitch, which is how to solve recurrences efficiently. So this is, I guess, hearkening to calculating Fibonacci and doing it in efficiently. Any more? There's a request for me to split the windows, which I did want to do. So let me go ahead and do that right now. Here we go, and here we go. I'll have to be mindful not to take up too much space when I do these things. Any more notes? All right. It's been 2 minutes, so let's go ahead and get started. All right. So Last week, where I left off was we were basically looking through a bunch of recursive functions working on lists. And one of the examples I gave was the length function. And in general, there's a lot of so I think a good place for us to start is to talk a little bit about recursion, and in particular, like how we might go about doing operations on lists in Haskell. So where should we start this discussion? So what I want to start off with is I just want to talk about a few things that are pretty common to want to do, and then we'll implement them, and then we'll look at generalizing them. So let's take a look. So last time we looked at length and we looked at rev, and I want to write a different function today, which is add2. What does add2 do? Well, it takes a list of integers and it adds 2 to every element inside the list. So remember we talked about Haskell type syntax, right? So you've got these arrows. The left side of the arrow says what the arguments are, so it takes a list of integers. And then on the right side, it gives you a list of integers back, right? So the idea behind this function is I want to add 2 to every list in this question. And hopefully no one's had any problems like writing type signatures like this. Just stick it all on one line and you'll be pretty good. Okay, so let's write the implementation for this. So as we mentioned last time, the way that we define a function in Haskell is we write the name of the function, we write the arguments, and then we write something here. And as I mentioned last time, you can put an underscore anytime you don't know what you want to do, and Haskell will helpfully tell you, hey, you didn't write your entire program, and the thing that you left out has to have the type list of integers, which is pretty helpful, especially if you can't keep track of what's going on here. Okay, so we want to add 2 to every list, and so intuitively, right, like what that says is like if I get an empty list, I want to give back an empty list. If I get a list with one element, I want to add 2 to that element. I add a list with 2 elements, then I want to add one x to that one and to this one. And clearly this is a bad strategy for writing this function. So how are we going to go about implementing this recursively? And once again, the big idea, right, when you're thinking recursively is you want to think about what the base case is and what's the recursive case. So what's the base case? So the base case is whatever you do when there's sort of like nothing left to do. It's one of those cases where you don't need to make another recursive call. And when do you not need to make a recursive call? Well, that's precisely when you have an empty list, right? Because there's no more listy things to do. So that's our base case, and we're going to keep that. And then to write the recursive case, the general recipe, right, is you want to pattern match on the element in question. So here, list add2 takes a list, right? What is a list in Haskell? A list is some head of the list and then the rest of the list. And we do this pattern match that gives us x, which points to the top, and x's that points to the rest. And then we want to somehow write some implementation that does it, making reference to x and x's. So how are we going to go about doing this? Well, a decent bet if you don't know what to do, and hopefully remember in the last lecture I said you can define helper variables using the where clause. A common thing to do is, well, let's call list add2 on the rest of the list, right? So this is going to be our recursive call. Let's call these y's for the added 2's, right? So this recursive call goes ahead and gives us all of the x's, but with 2 added to them. And so now we have got a sequence of y's, which are all of the elements that I needed to do for the rest of the list. And I just need to do this for the x in question so that I have a list add2 of x colon x's, i.e. x with x's at the end. So how do I do that? Well, I'm going to add 2 to x, right? I need to actually do the addition at some point. And then I will go ahead and tack on the y's to the end. I don't need the, if you're feeling nervous about the parenthesization, you can add parentheses here. But in this particular case, I happen to know that colon has lower precedence than plus. So this will all work out. I go ahead and load this, and I can run this on a few things, and hey, it all worked out. Questions so far in either chats? So to recap, while you're chewing over your questions, right? How do I recurse? Well, first I think about what my base case is and what my recursive case is. And in general, when we're talking about lists, recursion will always look like, how do I handle the case when it's an empty list constructor? And how do I handle the case when it's non-empty? So I've got some element and then the rest of the list over, right? I'm going to do some sort of recursive call on the rest of it. I can't, by the way, do something like this, right? Like that's a recursive call, but it's kind of bad, because if I actually wrote code like that, then well, it would actually just infinite loop. And why is it infinite looping? Well, I said, well, you know, to compute list add 2 prime, you call list add 2 prime, and to compute list add 2 prime, you call list add 2 prime. So there's always a sense in which whenever you call recursively, you have to call it on something smaller, and x is certainly smaller than x colon x's, and so that's why it works out. Okay, I don't see any questions, so let's generalize a bit. So list add 2 is cool, and then, you know, your client comes to you and they're like, hey, I also want to add okay, so there's a sort of divergence in the tracks here. So I want to first go down the route that tells us about higher order functions and lambdas, but then I want to come back and I want to go back to recursion in more complicated situations, because this situation is kind of a really easy pattern. And because it's so easy, in fact, there's a lot of ways to do this in Haskell that don't involve actually having to write all this code out. So we're first going to look into that, and then I'm going to come back and talk about cases where it might not be so straightforward to, like, you know, use something like what we're going to see shortly. So list add 2 is cool, but what if I wanted to do like list mul4, right? And that's just something that takes a list of integers and returns a list of integers, but this time they're all multiplied by 4. And that just seems kind of like a pain, right? I don't really want to be having to write out all of this code. Granted, it's not that much code, but it's you know, a decent amount. I don't want to have to write this out every single time I want to do some operation on every element of a list. So in Haskell, we have a way to abstract in this situation, right? And this abstraction is called map. I'm going to spell it like my map, because there's actually a built-in map which does this, but we're going to go ahead and implement it for now. So what does map do? Well, clearly it wants to be some function that you know, transforms integers to other integers, but we want to somehow generalize over the concept of multiplying by 4 or adding by 2. So someone was like, hey, I want you to tell me more about lambdas, you know, like how do I do lambdas in Haskell? And indeed, what we want here is exactly a lambda. What we want is a function that describes what the element by element operation I want to do in this situation is. And so that function is can be written in Haskell like this. Let's take a moment and mull over the type signature in this situation. So what is this saying? So it's saying that my map, well, it takes 2 arguments now. Because I said earlier, and I'm repeating this again because it's very important to know, there's all these arrows, right? And the last arrow leads to the output, and then every other element before is just a argument to the function in question. And we're going to resolve this. Why is it written this way? We're going to resolve that question very shortly. So it takes 2 arguments, okay? The second argument is one we've seen before, right? It takes a list of integers as the argument. But what does this say? Well, we've already talked about how we define the type signatures of functions, right? We define the type signatures of functions by saying a bunch of arrows. So this type has an arrow as well, and it's a int arrow int. So what this actually is saying is, hey, my map takes an argument that is a function that transforms integers to integers. So what does my map do? It takes a function transforming integers to integers. It takes a list of integers, and it gives you a list of integers. That's kind of a mouthful, but the type signature in Haskell writes this very compactly. And indeed, I really like, even when I'm in not Haskell languages, if I'm doing any sort of higher order functionness, that is to say a function that itself takes a function as an argument, I really like writing Haskell type signatures because there's a very clear way of explaining what is going on, and it can be kind of confusing in that situation. So how are we actually going to write this function? Well, the flip answer is let's just use the built-in, but let's imagine that we didn't have the built-in, right? So we're taking 2 arguments, and we need to somehow produce a list in this situation. In Haskell, conventionally, whenever I have a function and I don't really know what it is, I'll just call it f. Haskell people love their short argument names. It's just something to get used to. And what is f? Well, we can actually ask GHC to tell us what is f. So here I left this hole, right? The hole is something that GHC didn't give me as an argument. I didn't give GHC telling it, what to do here. And so GHC is like, hey, there's a hole. You need to give me an integer somehow. And by the way, the relevant bindings, aka the variables that are in scope, well, x's is a list of integers because you bound it as an argument, and f is a function from integers to integers. So let's go ahead and copy paste our implementation for the previous list add 2 here. And it's going to be wrong, but we're going to fix it up very shortly. And I'm just going to inline wise because I don't actually need to, write it out of line. There's only one use, so there's no help in doing it this way. So how did my old implementation of list add 2 work, right? I said, well, if I have an empty list, I'm just going to have an empty list. And if I have x colon x's, I'm just going to add 2 to the x and then cons that using the colon operator. I'm going to add that to the mymap list. Remember, we construct lists this way, right? So it takes on the left side an element and on the right side a list that you're going to put that element to the front of. So really what I want to do is I want to get rid of this x plus 2 and replace it with whatever arbitrary operation that I want to do in this case, i.e. adding 2 or multiplying by 4. So let's just go ahead and do that. Remember how you call functions in Haskell, right? You just call functions by putting the function and a space and then x. And for those of you who are still a little wobbly about precedence, right? This is equivalent. And you can write your code this way, and we won't dock points for that. If you're worried about when things are parenthesized or not. And so what we see here, right, is now instead of calling x plus 2, f is a function. So I just call it in the same way that I did recursive calls. So I call fx on here, and then I have my map x's. And this indeed does not type check. Why doesn't this type check? Well, it's okay. So I know what the reason is, but let's just walk through this. So when you write something wrong in Haskell and you get a type error like this, your first instinct, especially if you ever have written any C++, is to be like, oh no, there's so many error messages. What am I going to do? And I think Haskell type error messages can be pretty useful. And so they're worth actually taking a look at. So let's go ahead and look at the error message here. So what's going on here? So it's already pinpointed us a line, which is helpful, although we were working on line 29 already. And it says, hey, couldn't match expected type list of integers with actual type list of list of integers. And then it also helpfully says probable cause my map is applied to too few arguments. So what's going on here? Well, let's just look at our code. So the colon operator is expecting us to get a some sort of list on the right-hand side, right? And it's saying, hey, the expected type is a list of integers. So exactly what, when we look at our code, that's what we expect. But now it's telling us, actually, my map is a list of integers to list of integers. How come? Well, let's look at the signature again. So my map takes 2 arguments, and I've only given it 1 argument, and somehow Haskell is telling me that when I give 1 argument to a function in this situation, it's not ill-formed, it's not a syntax error, it's not I don't get the error message saying you didn't pass enough arguments, although it does say, hey, you probably didn't apply enough arguments, but it's telling me, hey, yeah, this is going to be a list of integers to integers once you pass an argument to it. But hopefully we can see the error of our ways. And we were supposed to, call mymap with f as well, right? Because mymap needs to take a function first and then a list. And so once we reload in this situation, we actually get the correct result. Checking for questions. What are your questions? So I'm just going to go ahead and give an example. Whoever asked for lambdas, how do I write lambdas in Haskell? So to write a lambda in Haskell, remember we did the JavaScript lecture and we were like, well, there's this arrow notation thing. So in Haskell, what you do is you say a backslash. Why a backslash? Well, it kind of looks like a lambda. So, that's what they picked for setting up lambdas. And then you write your arguments, you write an arrow saying, okay, I'm done with arguments, and then you say what you want it to do. So this lambda says, given an x, give me x plus 2. And so when I run it on 2, 3, 4, I get 4, 5, 6. And now I can do mul4, and it will multiply by 4. Still waiting for questions. Questions. Okay, so I've got another divergence, which is I just want to talk about currying real quick. What's currying? So I mentioned this weird thing, right, which is that when I call a function with not enough arguments, I don't get a, you didn't pass enough arguments. GHC will happily do that. And somehow I get back a function in that situation. And so I want to look at this in a little more detail. So to make this a little clearer, I'm just going to redefine add, which is our, bog simple, take 2 arguments, add them together, done, right? I don't want the infix notation mixing us up in a situation. So what's the type signature of add? Here we go. Okay, so previously I did this error where I didn't pass enough arguments, right? So when I pass enough arguments to add, things look pretty normal, right? Adding 2 and 5 is 7, and the type of that is an integer. All right, so what's going to happen if I don't pass enough arguments to add? Okay, that's a kind of weird error. No instance for show int arrow int arising from use of print. So what's going on here is that Haskell, when it prints stuff to the REPL, like 7, there's this thing called show, and basically some types have show and other types don't have show. So you can only show things that have a show instance associated with them. We'll learn more about this when we do type classes. But what GCI is saying is, hey, int to int, I don't know how to show that, so I can't show you in this situation. So let's just ask real quick what the type of this is. So what's the type of add3? Well, it's a function that takes integers to integers. So what do you think this function does? And luckily for us, we just wrote this function mymap, which takes integers to integers and then returns, and then takes a list of integers and produces a list of integers. So like, what if we go ahead and, feed in add3 to that situation? Aha. So what we've seen is when I pass add3, there's a weird thing that doesn't have enough arguments to mymap, then I see 2, 3, 4. There's a question in Twitch, which is, can this be thought of as a partial in Python? And that's exactly right. What is happening, and now I'm going to just give it away. What is happening is we are partially applying add with not all the arguments that are necessary, and we're getting a closure that basically is add with those arguments that you partially applied and waiting for the rest of the arguments that you want to give, right? Like we remembered that we had added 3, and so then later when we try to add with 2 inside mymap, we get 5 in this situation. So let's just let's play around with this a little. So one question is, so what's going on with this type signature, right? Why are there all these arrows? And so now what I'm going to tell you is that in fact these arrows are implicitly parenthesized. So this is a more accurate description of arrows in Haskell. And what's going on here is that add is not a function that takes 2 arguments and produces an integer. It is in fact a function that takes an int and produces a function which takes integers and produces integers. And so that explains why when I only give 3 to add, I get a function back, right? Because that's exactly what I said. And there's a sort of sleight of hand, right? Because if this were JavaScript, I would say something like add open paren 3 and then add open paren 4, right? And it would become very obvious that there was this like sort of higher order function business going on. But in Haskell, function application is just space, right? And so the spaces associate to the left. So when I say add 3, 4, really what I'm saying is, well, first partially apply add with 3 and then apply 4 as the next argument to it. I'm just going to write this down because it's important enough. Arrows associate to the right, A arrow, B arrow, C. Spaces associate to the left. Because I remember someone was, mentioning syntax, and like knowing the associativity of things in Haskell, that's a really important step to like feeling fluent with stuff that's going on here. Now, I don't expect you to memorize this, at least not yet. Once you get to lambda calculus, it'll be helpful to like have this internalized. But that's what's going on under the hood. So another way of putting this, and this is where this term currying comes from, is that all functions in Haskell are what we call implicitly curried. When you write a function that takes multiple arguments, in fact, you are defining a function that takes the first argument and produces another function that takes the next argument, that and so forth until you get to the output. And that's the normal way of writing functions in Haskell. In fact, we can write functions in the sort of traditional way, i.e. you're not allowed to partially apply them, and that can be done with something called tuples. I didn't tell you what tuples were in last lecture, so let me tell you what tuples are today. So tuples are just ways of putting, elements that maybe have different types together. So for example, 3 and true, well, they have different types. And so when I put them together like this, what's the type? Well, it says, hey, this is a tuple that contains a string as the first element and then a Boolean as the second element. And you can put as many things as you want in the tuple. And I'm annoyed, so let's just make this nice, and it's an integer for that. And unlike lists, tuples are heterogeneous, so they can have any element you want in them, and they also like are sort of weird, right? Like they don't do recursion, right? Once I have a tuple that has 2 elements, I just want to, for example, if I want to get out the elements from them, I can just pattern match on them in this situation. So if I do this, for example, x is AF and y is true. I don't have to worry about the tuple suddenly getting another element, because if the tuple had another element, it would have a different type, right? It wouldn't be a string and a bool. It would be a string and a bool and an int, a different type of tuple. So if I want to uncurry add, well, what I'm going to do, you might see the writing on the wall. I'm just going to take a tuple and then produce an integer. And, how did I say I can look at tuples? Well, I can just pattern match on it and then go ahead and do the same old thing that I was going to do before. And so I have this new function, add uncurried. And if you sort of hallucinate away that space, in fact, Haskell will let you get rid of the space. This looks very much like good old-fashioned function invocations that you might see in other languages. But don't do that, because in Haskell, it's idiomatic to write all your functions in curried style, and there really isn't any reason not to. You might be thinking, oh, isn't it inefficient to like keep creating all these intermediate functions? But GHC is actually smart enough to not do that when we're actually looking at the actual code. Okay, what are your questions? There's one last point I want to make, which is that this MyMap, there's no reason it really has to only work on integers. Like, I haven't really done anything using the integeriness. So using these type variables, we can say, okay, I don't really care about it being an int. It can be anything you want it to be. And I'll just call that A. So this is polymorphism. And it just says, hey, it doesn't matter what type you give me, right? I can do, say, not. Well, let me remind you, not is a function that takes bools to booleans. So I can like do this on a list of booleans, and that would also be reasonable as well. In fact, I don't even need the types of the input and output lists to be the same. They could actually be completely different. There's no reason to force them to be the same. So I can generalize this type signature even more, saying like for any A and for any B, any type B, if you give me a function that takes A's to B's, I'll give you a function that takes lists of A's to lists of B's. Remember, it's curried. So another parenthesization of this looks like this. And that'll work too. And now I can do something like, well, show is a function that takes integers to strings. So if I've got a list of integers, then I can convert them each into strings, and that also works. And this, in fact, is the type of map in the basic library. So if you want to do that, you can do it this way. One more thing, if you don't like writing, lambdas like this, there's another way you can go ahead and do the mapping, and that's called using a list comprehension. So what's a list comprehension? Well, it's another syntax for doing maps and similar types of things. And I'm just going to write out what it looks like for this example. In fact, you might be familiar with this syntax because many languages have list comprehensions, and they're a very convenient way for doing certain types of list operations. So what I've written here, well, here's a list comprehension, and there's this pipe. So let's just look on the left-hand side of the pipe. So the left-hand side of the pipe is basically saying what I want each element of the list to be, right? So if I'm like thinking about this as like these brackets are denoting a list, then I'm saying, well, I want a list whose elements are x plus 2. The pipe is sort of like saying, and here's how I'm going to iterate to generate the list. And then I'm going to say where x takes on the values of every element of this list, 1, 2, 3. So, now I'm going to say x plus 2 for x in 1, 2, 3. And that gives me 3, 4, 5. And that's list comprehension, and it works pretty good for map. And one of the really useful things about list comprehensions is you can do like nested iteration. So for example, let's say I had a list of lists, and I wanted to like flatten this list so that I just had 1, 2, let me just see. Just wanted 1, 2, 3, 4, 5, 6, none of the inner lists, right? So what I could do is I could say, okay, well, first I'm going to get a bunch of x's. So for each element of this list, assign it to x's. So x's will take on 1, 2, then 3, 4, then 5, 6. Then I'm going to be like, and then for each x's, element in x's, range over it as x. And then I want the final list to have the value x. And if I go ahead and do that, I have in fact flattened this nested list of lists into a single list. How do you do that in using map? The answer is you can't, right? Like if I did a map, well, what exactly would I put in the lambda, right? I can't put in x's because I can't exactly do this. Because that'll still give me a bunch of recursive lists. And in fact, there's just another function called concat_map, which goes ahead and does the concatenation. But I'm getting ahead of myself. We'll talk about this more when we talk about monads. Okay, so that's it for our divergence on sort of generalizing things in Haskell. I just want to talk a little bit about the big picture before we move on. So the big picture here, right, is that in Haskell, we don't really satisfy ourselves with writing boilerplate code over and over again. We really don't want to be doing that. And you can see that through various iterations, right? This thing that, admittedly wasn't that long, it was 2 lines, we could boil it down into a single function that handled basically it in any situation. And the tools we needed for that, we needed a lot of tools, right? We needed this concept of polymorphism in the type system so that we could, write this very generic function that really didn't care about what, the operation f you want to do in this case was. We needed higher order functions so that we could actually take f as an argument. And, we actually are also kind of, we use a lambda for this case, but it's often, people don't write lambdas when they're mapping because they'll just partially apply a function, and that gives them a function that, can be used then on every element of the map, right? So like map add 2 works perfectly well for mapping, and you don't even need to write the lambda in this situation. This is, by the way, equivalent to writing this. So like we need a lot of tools, but put together we have this way of writing things that is very short, and we can use it in a lot of situations. And there are a bunch of other functions that fall in this category as well. For example, filter is a function that takes a Boolean predicate, that is to say a function that looks at some element and returns true or false, and then it only returns the elements of a list that for which this is true as opposed to false. This is not so easy you can't do this with map. But once again, you don't want to be writing this code over and over again. And so filter is a single, function that you can just use in this situation. By the way, you can also filter in list comprehensions. So like say I wanted to return a list of x's, but only if x was even. Take it on my word that even is a function that returns bool if the number is even, and that will go ahead and do the filtering. So instead of doing another assignment, I just went ahead and put a Boolean expression here, and that'll do a filter. Questions? What are your questions? I'm gonna check on have I got the stuff. Okay, I'm going to do a shout out to the person who wrote syntax. Was there any particular syntax you wanted to look at? Arrows. Arrows in the function signature? Yeah, so let's just briefly go over this again. So whenever I am writing things in here, the arrows, how do I put it? The arrows bind sort of the least tightly of anything. So let's just go back to this signature, right? So what if I had forgotten to write the parentheses here? So I've forgotten to write the parentheses here. What do I have now? Well, let's try to read it, right? So I've got an A, arrow B, arrow list of A, arrow list of B. So this is a function that takes 3 arguments, an A, a B, and a list of A, and then produces a list of B. So that clearly isn't what I want, and Haskell will complain at me if I mess up in this situation. So I have to disambiguate it by putting parentheses. So whenever you, the rule of thumb is if you're ever writing a higher order function, you're going to need parentheses in it when you're writing your type signature. But for anything else, you don't really need parentheses because you can add them. It won't really hurt. This will be accepted just fine by the compiler, but they're not necessary. Did that answer your question about syntax? Cool. Okay, so as I promised, I promised to look at some situations where recursion is not so easy. And so I want to look at the implementation of a peculiar function called transpose. So what is transpose? So transpose is going to be a function that takes a list of lists and returns, once again, a list of lists. But those lists will be transposed. So transposition in this situation refers to the concept from linear algebra. So let's say that I have a list of lists. I'm going to write it here so I can indent it in the way that I want. Right? So here's my list of lists. If I want to transpose it, then I basically want to, flip it so that wherever I was reading off rows, now I'm reading off columns and vice versa. Now, claim, I can do this recursively. Really? Can you do this recursively? Might be a bit shocking if you're not used to doing recursion, right? Like if I were doing this in a imperative language and this was just some sort of array, I'd probably do some sort of indexing, right? I'd be like, okay, well, iterate through the rows and then iterate through the columns and index into the original array, looking at where things are. And indeed, you could write the function in that way in Haskell, but it wouldn't be idiomatic and it wouldn't be very efficient because indexing on lists in Haskell is actually an on operation. It's not a one. So watch out. So we're going to do this recursively. And I just want to like show you that, hey, yes, you can figure it out, but there might be some pit holes you need to navigate around on the way. In particular, we're going to have to write a helper function on our way. Well, let's take a look at this. So how are we going to write this function? Well, as I said, whenever I'm writing recursion, right, how to recurse, what is the base case? What is the recursive case? So I'm just going to type this out just to get me started, right? So I don't know what, so someone asked, is the recursive case a 1-by-1 matrix? That's an interesting idea, but because these are actually lists, so they don't even have to have the same length, for example, and we can still, well, it's a little tricky to transpose in that situation, but we're gonna still do it in this way. So the empty list case, now I'm wondering if I should do it by one. Let's go ahead and try this. It'll be instructive even if it's not right. So, okay, so let's go ahead. So we start off with this, and transposing an empty matrix is pretty easy, right? Because it's just an empty matrix. So what's going on here? Well, let me actually rename these a little, right? So when we're talking about a nested list of lists, the inside elements are all themselves lists. So I can't really, I don't really want to call them X. I'm going to call them X's. And then, the rest of everything else is a list of X's. This is also another common convention, which is you always just tack on an S in your variable naming when there's lots of lists involved. So what are we going to do here? So if we look at our example from up here, right? X's is going to be 1, 2, and X's is going to be a list of 3, 4. And we kind of have a problem, right? The problem is we can't really transpose 3, 4. Well, actually we can. So we could transpose it, and that would give us this, right? Because we're just transposing this rectangular thing, and so now we have a list of lists. So we're not really sure how we're going to use this yet, but let's just write it out because who knows, maybe it'll come in handy. What I've done here, by the way, is whenever I'm writing a recursive function, I get to assume that the function in question works when I call it recursively, right? I haven't actually written any of the important logic yet, but when you're like thinking about how to like set up a recursive function, it's really helpful to know what your function does like overall and just assume that it's going to work in that situation. So we just assume that it's going to work. So when I transpose XSS's, right, I have this rectangular matrix 3, 4, and I'm turning it into a vertical matrix that looks like this. Okay, so what I have now is I have these things, and I want to somehow get out the desired result. And what does the desired result look like? Well, it's the 1, 3, 2, 4, right? I want to somehow tack on the 1, 2 after these elements. How am I going to do that, right? Like I got this list 1, 2, and then I got this list of 3s and 4s, right? And the answer is, well, I need to do recursion again, actually. What I want to do, right, is go through every row inside the transpose x's and tack on 1 and 2 to each of those rows in questions. And in fact, there's a concept for this kind of thing in the standard library, and it's called zip. What does zipping do? Well, it basically pairs up elements of two different lists together. So if I zip a 1, 2, and 3, 4 together, I get a tuple of 1, 3 and a tuple of 2, 4. You can also zip in list comprehensions, and it looks like this. I think it's a pipe. Let's see if this works. No. Okay. There's some like language extension you got to turn on before you get it, or someone can go ahead and look this up later and tell me what it is. So this is helpful because what I want to do, right, is I want to work on 1 and list of 3, and I want to work on 2 and list of 4. But let's say we didn't have zip in our tool bag, and we just needed to somehow do this ourselves. We can do this ourselves as well, right? So I want to somehow combine x's and x-axis. So I'm going to define another function. So these where blocks, right? I can define functions inside word blocks. They don't have to just be regular functions. So what is combine going to do, right? So combine is taking, sorry, it's not x's, it's transposed. I'm going to head delete that for now. So we got this and we got this. So let's go ahead and give names to our variables. Once again, we're going to do recursion again. So we should do our base case and our recursive case. And how do I want to name this? I'll name these Y. And I'll make sure I put enough letters on them. So if I want to combine an empty list with an empty list, well, it's probably going to be some sort of empty list. I'm not going to think too hard about that for now. And now I need to somehow handle this case, right? Now it's getting a little hairy. There's a lot of things we got to deal with, and it can be helpful to like take a look at what's going on when I'm actually doing this. So let's take a peek. So remember I mentioned this thing called trace. Well, there's another version of it called error, and what error does is it just says, hey, you got here and I don't know what to do, so error. And whenever you're writing code and you're not interested in GHC giving you this like handy whole thing, you can instead write an error, or there's also a version that doesn't have anything called undefined, and you can basically just stub out parts of your code that you don't know how to write and get everything to type check around it, right? So if I actually try to call this on a non-trivial matrix, I'll get an error in the situation. Actually, I didn't even get here because, okay, I need to backtrack a little bit and explain what's going on with the pattern match here. So up until now, most of the pattern match examples I've given involved a single argument. And then with combine here, what I actually did was I wrote a pattern match that has, oh, I know why that happened. It has to be this. Oh no, this is not it either. Interesting. Oh, I'm not sure. Okay, well, we'll fix this very shortly. So, I wrote pattern matches and they only operated on a single variable, right? But we have multiple functions. We have functions that can take multiple arguments in Haskell. And when a function takes multiple arguments, we can pattern match on multiple arguments at the same time. So when I write combine empty list equals empty list, what I'm saying is that, hey, if the first argument is an empty list and the second argument is an empty list, then do this. And similarly, when I say combine x colon x's, I'm saying if the first argument is a non-empty list where, you know, the first element is x and the second element, the rest of the list is x's, and the second list is a non-empty list where the first element is y's and the rest of it is y's s, then do this instead. And so why is there an inexhaustive pattern match? Well, it's because I don't necessarily have to return a I don't necessarily have to have one of these be empty and the other one doesn't, right? Like I could have the first one be empty, but the second one isn't empty, or the second one is empty and the first one isn't empty. So let me just go ahead and generalize this a little. So what I'm saying now is if the first argument is empty, then return an empty list. And if the second argument is empty, return an empty list. And so we're only interested in the case when both of them are non-empty. And so now I can go ahead and run this and oops. Actually, we're done. So that's not quite right. Okay, I know why this is not quite right. And I want to explain how to get there. So we've gotten to this place where we put in some base cases. We thought they were reasonable. And in fact, when we write our function, it just returns an empty list. And we're like, uh-oh, that doesn't sound very good. So what can we do? Well, let's use our handy dandy trace to take a look at what is being called when we go ahead writing these functions. So let's print out what the value of x's is. Oh, this is yeah, this is useful because I need to tell you how. So what I'm going to do is I'm going to change this type signature to be a little more specific, because otherwise I can't show x's. Because if I say a, that means it could be anything, even if I don't necessarily know what it is. So here is x's, even if it's like a list of functions, and then I wouldn't be able to deal with it in this situation. B combine, it's not B combine, it's just combine. And let's take a look at what's going on. So first, when I call this function, I called it with 1, 2, and x's is 3, 4. And the second time I call this function, I call it with x's 3, 4, and xs's is an empty list, right? And so when that happens, when I transpose xs's, I get an empty list. And then when I try to combine them, well, that doesn't work. So this guy is not right, right? Because what's going on is I've got a empty list here, and then when I combine 3, 4 with an empty list, I'm saying that's an empty list, but that's clearly not right. What I wanted to do was I wanted to get my vertical 3, 4 in this situation. So let's go ahead and redo this. By the way, please shout questions if I'm going too fast or you've fallen off the wagon. Pausing for a moment. Take it in. So let's write a new version of this particular case. So once again, I have to do this in a recursive manner. And so I'm going to pattern match on x colon x's, and I'm going to think a little bit about what I want to do here. So if x's is 3 colon 4, then I've got a 3 and then I've got a 4. And what I want to do is I want to like sort of place the x in its own singleton list and then combine x's with the rest of the list, which it's empty in this situation. So what I'm doing here, and here it might be helpful to actually go ahead and make combine be its own top level function. So I can delete the where clause and stick it over here, and I'll give it a type signature because it's helpful to know what the types of these things are. You could have given it this type signature as well when you were here. And so now I can just go ahead and call this function directly on the example that I was looking at to see what's going on. And indeed, this is doing what I wanted to do. It went ahead and transposed it. And if you stare at the code a little, you'll see why this happened, right? What happened was for every element in x's, when y's was empty, I took that element, I wrapped it up into a list, and then I appended it onto a list of, well, the rest of them that were transposed in this way. And that gives me this nice, list of 3, comma, list of 4. So that looks pretty good. And so let's go ahead and go back to our main example and see what happens. So This works out okay. And then finally we got to this error, right? Because now I'm doing a non-trivial combination between 1, 2 and the transposes of x's. And so now I need to somehow do this situation. And it's going to look a bit similar, right? So what I want to do is I want to combine x's and y's, the recursive case, because, well, you know, I've got a bunch of, in this particular example, right, I'll have 2 and then I'll have 4. And so if I can get 2, 4 in that situation, that looks good to me. Is it 2, 4? Something. I don't think I gave exactly the right numbers. And what I want to do now is, instead of just having x by itself, I want to stick x onto the front of the y's list. So now we're done here. There's some type errors. Let's see what these type errors are. So could not match type int with list of int. The second argument of combine. And why is that? That's because x is an integer, y's is a list of integers, so I can get a list of integers this way. And the answer is, well, once I have a list of integers, if I wrap it up into another list, I have a list of integers. But if I then cons that onto another list, I have a list of a list of a list of integers. That's 3 lists of integers. So actually I don't want square brackets here, I want parentheses here. So meta point is, right, if there's a type signature like this, sort of working out like what you expect the types to be will often tell you, you know, where the error is. And so for me, like I often just figure things out by doing internal type checking. But reading the type signature would also have told us, right, that the expected type was, well, we were expecting a list of integers, and we actually got a list of integers. So now we're here, and hey, we have a working transpose. Questions? So let's recap on this journey briefly. So where did we start? So we started off with this, you know, seemingly hopelessly complicated situation where we wanted to write this function and we didn't really know how to go write it, right? Like we knew how to do it with indexing, but we didn't know how to do it with pattern matching. So what did we do? We just bravely sallied forth. We were like, okay, what's the base case? What's the recursive case? And while we were working on the recursive case, we realized, hey, you know, we've got some lists and we actually know what we want to do with them, right? Like if we looked at the concrete values in those situations, we could vision how we wanted them to be put together. But to put them together, we needed another function that did another level of recursion to do that combination in question. And so we wrote 2 functions, right? A transpose function, which just does the transpose, and a combine function, which takes in, you know, one of these transpose matrices that we're building and then sort of adds on one more column to the set of things we're writing, right? So like 1, 2, when added to the transposed list 3 and 4, puts the 1 onto the list that was 3 and puts the 2 onto the list that was 4. Maybe this is a little hard to see when you only have 2 elements, 1 element, but with multiple elements, you can see that the 1 got added on the front of the 3, 5 list and the 2 got added on the front of the 4, 6 list. Pausing a bit. Questions? Comments? Someone asked about recurrences on Twitch, and I'm not going to do those today. Come back again when we talk about lazy evaluation, and we'll have some fun with those then. This is a good opportunity to talk a little bit about the import statements. So this transpose function that I just talked about actually is in the standard library, but as you can see right now, it is not in what we call the prelude. The prelude is the set of all identifiers that are loaded by default when you're in Haskell. So map is in the prelude, not is in the prelude, but transpose is not in the prelude. It's actually in another module. So to get at a trace is similar, but we imported the debug.trace module, so that's why it's in scope. You can actually ask GHCI where things come from by using :info, and it'll tell you, hey, this is defined in debug trace. Although sometimes it'll give you a very strange answer, like plus is defined in ghc.num. What's ghc.num? You don't need to know. It's not useful. So the basic way of doing an import in Haskell is you just write the module name and it will dump everything that was in that module into scope, right? So debug.trace exports trace. So if I just say import debug.trace, then I will dump everything, including trace. If I want to be a bit more choosy and I only want to import stuff that I care about, I can use parentheses to explicitly list out the things that I want. So trace is still in scope, but anything else that was in that module isn't in scope. So for another example is this transpose function is part of the standard library, but it's in this other module called data.list. And so if I import data.list and say, hey, I want transpose, now I will get a transpose function that does exactly the same thing as what we just implemented. There's some other things you can do. So you can like import qualified. What that does is it says, don't dump all the names into scope, but instead dump them such that you have to explicitly qualify them with the name of the module they came from. There are some modules which are expected to be imported or qualified in this way, and you will see them later as we get further. And you can even give a shorter name so you don't have to type data.list every time. You could just say capital L in this case. That's really all we need to know about importing modules for now. Okay, we have 15 minutes left. I want to, let me just double check I've hit all the stuff that I want to do. And once again, questions at any time. Really interested in your questions. Okay, so what I'm going to do is I'm just going to go on a whirlwind overview of everything we've talked about so far about lists. And on Wednesday, we will talk about algebraic data types. I think I have given you everything you need to work on the lab at this point. It's due on Wednesday, reminder. Okay, so what have we talked about, right? So we talked about lists in Haskell. They are a very, very ubiquitous data type, so it's worth getting really comfortable with them. Okay, there are list literal syntax, right? Looks just like in other languages. You just use square brackets, numbers. There's a comment which is it's funny for transpose to when you don't have a fully when you don't have a rectangular matrix, transpose does something funny, and I agree, it does do something funny in that case. Actually, let me just run that example, and that's what you get in that situation. That's kind of weird. What does our transpose do in that case? Okay, it does the same thing, because I think we actually basically rewrote the standard library implementation in that case. You can step through it to figure out why it's like that. Okay, but these list literals are a bit of a misnomer because we're not doing arrays, we're actually doing singly linked lists. And when you have singly linked lists, there are two ways you can construct them, right? You can have an empty list, or you can, cons on an element to the list. The two ways of constructing a list in this way are also the two ways you can pattern match on them. So it's important to know what the constructors, these are constructors, in fact, and we'll talk more about constructors on Wednesday. So when we pattern match, we can only pattern match on the constructors, aka empty list and colon. By the way, you can't pattern match on, say, append, right? And there's two reasons. One is it's not a constructor, but two is like, how would you know how to split the list, right? Like what exactly, would you put on the left-hand side of the append and on the right-hand side of the append? We talked about how to go and operate on lists, right? And so our basic tool in the toolbox is recursion. So we just write a function that pattern matches on the empty list and the list of lists, the cons constructor, and then we just do recursive calls as necessary. Sometimes many occurrences of recursion. But often we don't want to actually write things recursively directly. And there are some higher order functions which capture what we call recursion patterns, right? Or methods of recursion that happen over and over again. And so we want to have a function that can just handle it for us so we don't have to write the code over and over again. And we looked at map, which we implemented. And we also looked at some other examples like filter and I guess zip technically counts as well. Zip width, I suppose. The operation that's going on here is basically a form of zip width. Although not exactly the same. Not exactly the same. And let me see. And hopefully I've shown you that in Haskell, we can write our code very compactly, even in this recursive style. It's a very different way of thinking, but it is really interesting, and you can go a long way working with lists in this way. Questions so far? Requests for any other topics we should go over here. Otherwise, I'm just going to implement some more functions. Okay, I'm gonna do another function. This function is called replicate. So replicate is in the standard library. And what it does is it takes an integer and it takes an element and it basically creates a list with that many copies of the element in question. So if I want 5 falses, then replicate 5 false gives me a list that has that many falses. So let's see how we would implement this. So I'm going to call our version replicat. In fact, I'm going to force folks here to help me implement this function. So replicat, what should I do? So I wrote down the type signature of this function. What should I do first? What did I do first with all the other functions that I wrote here? Type it in chat. Base case of 0. Great. Let's do a base case of 0. Thanks, Twitch. So if I want to replicate x 0 times, what should I do? Well, probably I don't want to return any copies of it, right? By the way, if an argument doesn't matter, you can replace it with an underscore, and that just means doesn't matter. I don't care about it. And so if we do the base case, then we need the recursive case. So what does the recursive case look like? Well, it's going to look something like this, right? So I've got my n, I've got my x. You can't pattern match on integers. So we're just going to call n minus 1 at some point, right? So the recursive case is going to be something like n minus 1 x. And what do we need to do? So once we've replicated x n minus 1 times, and we need x replicated n times, how do we get there? This will type check. What we've written so far, by the way, type checks, but it's not very good. Use a colon. Yeah, I like using colon. So we'll just tack on X to this list in question. And now we will indeed get true replicated 5 times. What if I did this? What does this code do? Well, we can just run it. And well, since we added X 2 times, every time we made N go down once, it just doubles the length of the replicated list. Okay, let's do another function. Let's do sum. So what is sum? So sum takes a list of integers and it sums them all together. And we're going to call ours SM because sum is in the standard library and so it's already defined. So if I have 1, 2, 3, right, I just want to sum them together to be 6. So how am I going to do this? Well, let's write a base case. If I sum together a list of empty integers, what is that? Well, I mean, nothing. And what I'm going to do here, well, let's go ahead and recursively sum the rest of the list. Just add X in this situation. Indeed, this gives us a sum. Actually, there's something even more we can do in this situation. So we looked at product in an earlier lecture. Did we do product? No, we did factorial. But factorial is also a good example as well. No, it's not, because there's no list involved. There's another function, right, called product, and what product does is it multiplies all the elements of a list together, also in the standard library. And there's a lot of, in fact, we could have done factorial implemented in this way, right, where factorial of n is simply the product of all numbers between 1 and n. These are all things I told you about, right? This gives me a list spanning the numbers between 1 and n inclusive on both ends, and then product multiplies them together. So I can very easily compute factorials this way. And there might be other ways you might consider in combining all the functions in this way. And so it can actually be a bit of a drag to have to write all these over and over again. So there's in fact a concept called a fold, which generalizes over this kind of operation as well. So to explain what a fold is, it's most useful to think about what the list structure looks like. So when I have a list like 1, 2, 3, as a data structure, what does this look like? Well, the list 1, 2, 3 is actually technically 1 cons onto 2 cons onto the 3 cons onto an empty list. Let me put in the parentheses for clarity. And you can write this like a data structure, which will look like this. So the concept behind a fold is, let's replace this with a bunch of function calls where I do a bunch of function calls wherever I had done cons, and I replace the empty element with some sort of base case, right? Because, you know, when I looked at sum and when I looked at product, those were the commonalities in those situations, right? There was some base case, and then there was some combining function which put them together. And so lucky me, there is a fold in the standard library, which has a, it's called fold R. It's got a fancy signature, but let me give you one example of a valid signature for it. So this is a valid signature for it. It takes a function, the combining function f. It takes a 0 element and it takes a list and then gives you it this in this case. And so for product and sum, we don't need to be that general. We just, have, well, somehow put the elements together, give me a value for 0 and give me a list. So let's go ahead and implement sum. So how do I want to combine things when I'm summing together? I want to add. What's my 0 element? It's 0. And then let me just give it some list. And hey, I got the sum of all these elements. Well, you wouldn't be able to tell if that was a product because I didn't put enough elements, but here, definitely a sum. And how do I implement product? Well, instead of doing a plus, do a multiply. By the way, reminder, when I put parentheses around an infix operator, it turns it into a normal function. So that's why I'm able to do it here. And hey, I've got a product as well. There is something to be wary about here, though, which is that actually this will be implemented very inefficiently. And you should use this thing called fold L prime to do folds in this situation, which will actually, it looks the same, but it actually is different because there are efficiency considerations. But if we're just talking about like morally what's going on, and especially when we talk about algebraic data types, this concept of a fold is a really interesting and useful one. Okay, we are out of time. Thanks everyone for coming. See you on Wednesday. So I'm gonna stay around to just answer questions. There's one question: would fold L generally be more efficient than fold R for Haskell lists? And the answer is it depends. For this particular answer, example of summing and producting, you don't even want fold L, you want fold L prime. And the reason for the prime is because of lazy evaluation. So there's this lazy evaluation thing going on, and if you wait until later to evaluate things, that causes a problem. It's actually related to that thing I mentioned in an earlier lecture, where when you have laziness, you might end up with a big string of stuff you haven't done yet. And it would have been less work for you if you'd just gone ahead and did the work immediately. And that's what that little prime is about. It's about doing things eagerly. But there's other situations where you don't actually need everything all at once. And then fold R is useful and actually the most efficient thing to do in that case. So it leads a little bit more knowledge about laziness, which we're not getting to until halfway through, to know when you should use one or the other. Well, there's not really such a thing as fold R prime, I think. Yeah, there's no such thing as fold R prime. And there's also a reason for why that's the case as well. The short answer is fold R is sort of very lazy because it preserves the structure of the list as you go along. Whereas fold L prime actually goes ahead and reassociates the function calls. So instead of F1, 2, 3, we do 1 and 2, 1 with the 0 element first, then 2 with the result of that, and so forth. They're called left fold and right fold because, as you can see here, it looks like we're going off to the right, and then the left fold looks differently. We're going to go off to the left instead. I'm not. There are diagrams online if you look up fold L and fold R, and maybe I can just pull one up. Yeah, this looks like the diagram I want. Yeah, here you go. So fold L puts it the other direction. All right, thanks everyone.